So now that we've introduced inductors, what we're going to come back and do is basically look at what we know about capacitors and what we know about conductors and see how very similar they are, but then some fundamental differences. So let's start by thinking about capacitors again. We said, well, we know that we make a capacitor by taking two conducting surfaces. So here's a conducting plate, here's a conducting plate, and you just stick an insulator in between. If that insulator happens to be air, fine. If it's anything besides air, that gets referred to as a dielectric. That's just going to change what the capacitance is. And then the capacitance is what we're keeping track of. And again, this is really just dependent on the geometry of how you build your capacitor. We said we know that a capacitor is going to store energy within an electric field, and it's going to do it by this expression, 1/2 C times whatever the voltage is across your capacitor squared. So here's how the electrical energy is stored within a capacitor. And then we know that the capacitance is measuring the charge stored at a given potential difference. So again, the capacitance is just going to be the ratio between the charge stored on your plates and the potential difference across your plates. So this is sort of fundamentally kind of the key idea is defining a capacitor. Well, what are the key ideas defining an inductor? Well, we said one, again, how do you build it? Well, you wind wire. So you're winding wire around some core. And again, this can be an iron core, which is going to increase the flux going through that's being captured by your windings here, or it can be air or something that's not iron, which wouldn't affect the magnetic flux. Again, what we're measuring here is the inductance, and the inductance, again, is basically just dependent on how you sort of wrap this thing around. Again, what's the geometry of how you've built your inductor, and then what, if anything, you've sort of included in it. We said we know that an inductor is going to store energy within a magnetic field, and again, the expression we use to calculate that is going to be 1/2 L, the inductance, times the current squared. So one of the things that you should pay attention to is what you're going to see pretty consistently is that we have replaced C with L, so capacitance with inductance, and we've replaced voltage with current. And those two sort of swaps are going to be pretty consistent across a lot of these comparisons. So where we would say this is what's going on with the voltage for a capacitor, we're going to come back and say, this is what's going on for the current with an inductor. Again, fundamentally, sort of our key equation defining an inductor is that it's measuring the magnetic flux through the inductor at a given current. So again, as these things wind around, right, basically what we've done is we've created a solenoid. There's going to be a magnetic field that comes up through this. That magnetic field is going to generate a magnetic flux through these windings, and so as you change the current, that's going to change the magnetic field and therefore change the flux. Right, so that's the idea in terms of what we're measuring with inductance. All right, and then just some fundamental ideas here. So one, we said the defining equation for capacitors that sort of tells us what's going on is that the current, as you're charging or discharging a capacitor, so again, this is kind of thinking about capacitors and inductors within transient circuits. So the current that's discharging or charging or discharging your capacitor is given by, well, that's just its definition. And again, we know that, Q is just C times V. The capacitance is a constant, so I can think of the current as nothing more than just C times the time rate of change of the voltage. What that equation is telling us is that capacitors resist changes in voltage. The current can change quickly, but the voltage really doesn't. So what that means is, in some sense, that before you can build up a potential across your plates, you have to have a current that's going to put charges on them. So it's sort of, the current has to come first. Now, one of the things that we'll sort of key on with transient circuits is thinking about behavior at t equals 0 and behavior as time approaches infinity. And so at t equals 0, a capacitor, it just acts like a wire. But as t approaches infinity, which is another way of saying that your capacitor is fully charged, then your capacitor acts like a battery that's trying to drive current in the opposite direction. So effectively, it acts like a broken wire. It stops current flowing within the branch where the capacitor is located. So these are sort of fundamentally what's going on with capacitors in transient circuits. In inductors in transient circuits, again, there's a defining equation. And you notice what has happened here is that we've said, oh, well, this is the back EMF generated by the inductor is going to be equal to the inductance times the IDT. So you'll notice I has been replaced with V, V has been replaced with I, C has been replaced with L, and basically I've gone from my defining equation for capacitors to my defining equation for inductors. So what is this equation trying to tell us? Well, it's trying to tell us that inductors resist changes in current. So an inductor wants the current to stay what it was before. And so in order to get the current to change, you have to start, right? The current will start changing and you'll have a back EMF. You'll have a back EMF first and then you'll see differences in the current. So this is, again, in this case, we said that you got to have current for the capacitor. We said you've got to have current before you end up with a potential difference building up across your plates. For an inductor, what you're going to see is initially we will have a back EMF that keeps current from changing, and then that back EMF will die away and your current will change. So currents don't change quickly for inductors. Voltages don't change quickly for capacitors. Again, thinking about behavior at t equals 0 and behavior as t approaches infinity, well, at t equals 0, an inductor acts like a broken wire. Again, really what it's going to act like is it's going to act like a battery that's generating a back EMF that will keep the current from changing within the branch of the inductor. So it's going to act like a broken wire. And then as t approaches infinity, eventually, as t approaches infinity, your inductor no longer has a back EMF, and so it just acts like a wire. So these are kind of fundamentally, and again, you'll notice that we're switching when a capacitor acts like a broken wire versus when an inductor acts like a broken wire. We're switching whether you're resisting changes in voltage versus changes in current. So there's clearly a lot of analogies between these two circuit elements, but we've got to be clear about which one cares about just sort of what these details are in terms of thinking about what's going to change first, what it's going to act like at t equals 0, what it's going to act like at t approaches infinity.